Hi, my name's Jan, and I'll be presenting our work on formally verified high-level synthesis. Field programmable gate arrays are good alternatives to CPUs for many applications because they can be specialized to the target application. However, they can be quite difficult to program because of this, as they implement the hardware circuits directly. High-level synthesis can help with this by transforming software code into hardware descriptions. The flow would then resemble something like the following. First, the code would be translated from C to Verilog, a hardware description language. Then, the Verilog hardware description would be placed onto the FPGA using a logic synthesis tool. One caveat, though, is that current HLS tools are quite unreliable. We managed to find bugs in most of the current HLS tools. We then also tested our verified high-level synthesis tool Verisert using similar test cases, and apart from a bug in the pretty printing, we did not find any other runtime errors. Our formally verified HLS tool called Verisert leverages CompSert to transform C to Verilog in a verified manner. We branch off at the 3AC stage, also known as RTL in the CompSert literature, going to an intermediate language called HTL, which is based on finite state machines. On HTL, we can then also perform some light optimizations. Finally, we transform the HTL state machine to Verilog. Comparing execution time against an existing HLS tool called LegUp, we found that Verisert generated designs that were normally similar in size, but they were around 27 times slower when divisions were present. However, the better news is that if divisions are replaced by an iterative algorithm in C, then Verisert is only about 2 times slower than optimized LegUp, and on par with LegUp without optimizations. So now I'll go over a quick demo about how to compile a really simple C program using Verisert into hardware, and then how to simulate that hardware and see that it is the same as executing the C code. So we're going to compile this very simple C program in this case, which just assigns 0 to an array, sets one memory location to 2, and then returns that memory location. And we're going to compile this without optimization so that we actually get all the loads and stores. So to compile this C file, we then use Verisert, and in this case, without any optimizations, and we want to print the intermediate RTL so that we can see what CompSert generates. And then finally, we take in the C file and output a Verilog file. So now we have plenty of RTL files, which are the intermediate files that CompSert generates, and then finally the Verilog file, which we generate. So having a quick look at one of the RTL files, we can see that because it ran without optimizations, it performs all the stores, and then finally returns the value in memory. And so now we can have a look at the actual hardware that was generated. So we first have a lot of register declarations, and then we have a block which simulates the RAM block and is used to ensure that we actually use the RAM properly. We then have a data path where in each state, we then assign a value to the registers. And in case we do, for example, in this case, we do a store, we instead actually have to use the proper RAM signals and do a proper store according to the RAM interface. And then finally, we have a block which represents the state transitions. And in the end, we also just generate a quick test bench, which will execute the main hardware. And it will then, at the end, print the number of cycles when the finished signal is high. It will print the number of cycles and what the value in the return is. So we can simulate this hardware now using an open source simulator called Icarus Verilog. So we use Verilog. We take the system Verilog file and we want to output a small binary which will simulate the actual hardware. And we can then execute that, and it prints out the number of cycles and the final value, which is 2, which is the value it should be expected. Thank you for listening. And if you're interested in knowing more about Verisert, please have a look at our OOPSLA 21 paper or our poster. Thank you.